Okay, hello everyone. So today we are going to present our research. Title is a comparative analysis of backtracking and dynamic programming in solving the 01 knapsack problem. So this study is conducted by me, Ismadudin W. Marta, 2415101054, and my friends.
And my name is Afra Putri with last digit of student ID 064.
Okay. Next. So what is the 01 knapsack problem? So it is a famous puzzle in a computer science. Imagine you have a bag or a knapsack with a weight limit. You have a set of items, and each item has a specific weight and a specific value. Your goal is to fill the bag to get the highest total value possible without going over the weight limit. The 01 part means you have a simple choice for each item. Either you take Either you take it is 1 and you leave it is 0. You cannot take half of an item. Next. Okay, this is not just a math puzzle. It has a real world uses. For example, in logistics, companies like GNT Express or Si Cepat need to decide which packets to put in delivery truck to maximize the value of the shipments. It is also used in budget planning, where you have a limited money and want to choose the best project to fund and in supply chain to efficient allocating limited storage resources across various product categories to ensure profitability. Next. So this is our algorithm. We use backtracking and dynamic programming. The first algorithm we studied is about the backtracking. Think of this like exploring a maze. The algorithm tries every possible. If it sees that a certain path will go over the weight limit, it stops, goes back, and tries a different path. This is called pruning. While it always finds the best answer, it can be very slow because it has to check so many combinations. Next. And the second algorithm is about the dynamic programming or DP. DP is much smarter. Instead of trying every combinations, from scratch, it breaks the problem into smaller pieces. It solves those small pieces and stores the answer in a table. This way, if the algorithm needs the same answer again, it just look it up instead of recalculating it. This tabulation method saves a lot of time. Next. So, let's look at how these two algorithms actually work behind the scenes using pseudocode. On the left side, we have the backtracking algorithm. It uses a recursive helper function called solve. It checks each item one by one. If adding an item fits within our maximum capacity, it moves forward and adds the item's weight and value. If it doesn't fit, or if it finishes check all items, it backs up and tries the alternative path where the item is left behind. It keeps updating the best value until it finds the absolute best combination. On the right side of pseudocode is the dynamic programming, which is much shorter. Instead of using recursion, it uses loops. It creates a simple list of array called DP to store the maximum values for every possible weight capacity. It loops through each item and updates the table from the maximum capacity down to the item weight. By doing this, it builds on top of previous answer and at the very end, it simply returns the final answer stored at DP capacity. Next. So in here, we compare the two algorithms side by side. From the time complexity, backtracking is exponential O to power n, and the dynamic programming is pseudo-polynomial O and W. And for the space complexity, backtracking has a minimal O n, and the dynamic programming has a various OW 1D optimizations. And the third type, the backtracking, is a exhaustive DFS with pruning, and the dynamic programming has a bottom-up tabulations. On the scalability, backtracking is very low, and the dynamic programming is high if the way is manageable. In short, both algorithms will give you the perfect optimal solutions, but dynamic programming is designed to be much more efficient as the problem gets bigger. And the next explanation will be held by my friend.
Okay, thank you, Dinda. Now let's look at our experiment. So all tests were run on my device with 16 gigabits of RAM, and both algorithms were implemented in C programming language and compiled with GCC. And then we use the PISINGER large coefficient benchmark dataset, which is a standard international benchmark for Knapsack research. So we run two experiments. The experiment one is compares both algorithm head to head at n equals 15, 20, 25, and 30. And experiment two tests only dynamic programming at larger size, n equals 50, 100, 200, and 500. Okay, so here are the results of experiment one. So at n equals 15, both algorithm finished correctly, but backtracking is already 29 times lower than the dynamic programming. At n equals 20, the backtracking takes 0.4 seconds, while DP finishes in less than 1 millisecond. At n equals 25, the backtracking takes almost 30 seconds. So that is uh 300 times lower than dynamic programming. At n equals 30, backtracking hits our 30 seconds time limit and fails to complete. Meanwhile, the dynamic programming finishes at 4 size in under 1 millisecond. So importantly, for all cases where backtracking did finish, both algorithms produce the exact same result, confirming the correctness. So this is the chart user logarithm scale on the y-axis and better show the dramatic difference. The red line is the backtracking, so you can see it shoot up sharply as an increase. So the green line, the blue line is the dynamic programming, so it stays almost flat because it's barely moving. So we exceeded n equals 30 for backtracking because it did not finish. So this charts clearly show exponential growth in backtracking versus the near flat line of dynamic programming. So this is the experiment tool that we're doing. It's DP stand for dynamic programming scalability test. So the programming alone on a larger input size at n equals 50, DP finishes in under 1 millisecond. Even at n equals 500, 10 times bigger, dynamic programming only takes about 8 milliseconds, and the growth is nearly linear, consistent with O of n times V, uh, sorry, W, where W is fixed at 10,000. Backtracking cannot even start these tasks. They would take years to complete, so this experiment confirms that dynamic programming is highly scalable and ready for real-world use. All right, so as for the conclusion, so to wrap up, we have three main conclusions. The first one is the performance gap is real and dramatic. So backtracking grew for 0.028 second at n equals to 25. That is 30,000 times slower than dynamic programming. At n equals 30, it completely failed. So the second one is dynamic programming is highly scalable. So the growth follows our expectation of O of n times V completely. The third one is both algorithm always find optimal. So dynamic programming is not just faster, it's equally correct. So our final recommendation is we use dynamic programming for the 0, 1 knapsack problem. So for the close, I will give it to Dinda.
Okay, I think that's all our explanations about our article. I think that's all from us. Thank you.